In the last lesson, we looked at how ions can form by the gain or loss of electrons, and gaining or losing electrons helps atoms become stable. But that can't just happen in isolation. If an atom loses electrons, those electrons have to go somewhere. And if an atom's going to gain electrons, those electrons have to come from somewhere. In this lesson, we're going to see where those electrons go and where they come from. And so it's actually in the formation of a bond that electrons are transferred, the formation of an ionic bond. Now, we looked at this a little bit last time. We know atoms want to gain or lose electrons to reach a stable electron configuration, and that's actually why they bond. They bond to reach that stable electron configuration, and one of the ways they do that is transferring electrons. So we know in groups 1 through 7, they have incomplete outer levels. Either they have too many electrons and they're up too far, or they don't have quite enough and they need to get a few more electrons to fill their energy level. The ones in group 8 already are complete. They don't need any more. That's the noble gases, remember, and the noble gases do not form bonds. So we don't worry about the noble gases here, but the other 7 groups will bond. And so they'll form a compound. Remember, that's 2 or more different elements bonded together. So salt, which is sodium chloride, is the combination of sodium ions and chlorine ions stuck together. And they stick because they have opposite charges. Now, oxygen gas is just oxygen. It is 2 atoms of oxygen stuck together. They are bonded, but because they're identical elements, it's not a compound. So let's get into ionic bonding. An ionic bond is formed when valence electrons are transferred from one element to another, and that creates a charged atom, and those charged atoms will then attract, because if something gained an electron, it's negative, and if something lost an electron, it's positive, and oppositely charged particles will attract. So because metals form our positive ions and nonmetals form our anions, or negative ions, we get ionic compounds that form between a metal and a non-metal. So like I said, salt, which is sodium chloride, there's our metal, and there's our non-metal. Now, look at your name on this. Ide refers to the fact that this is in a compound. It's the ion of chlorine. Sodium metal, which is going to form a sodium ion, is going to combine with a chlorine ion, and we get sodium chloride. That ending changes to IDE to denote that, yeah, it's in a compound now. So if we look at this a little more detail, an ionic compound is a compound made of ions held together by ionic bonds. Now, an ionic bond is an attraction between oppositely charged particles. That's all a chemical bond is. It's an attraction between atoms or ions. An ionic bond is an attraction between oppositely charged ions. Now, these ions will arrange so that the opposite charges stick together. This is what this picture shows down here. You notice next to every negative is a positive, and next to every positive is a negative. The overall crystal, this whole thing, will have an equal amount of positive and negative charge, so that overall the crystal is neutral. And that's true in ionic compounds. The crystal that they form has an overall neutral charge. And you could keep throwing ions into this and getting the crystal bigger and bigger, as long as for every positive there's a negative. Now, the name of the compound tells us what ions are in it. Now, we're pretty much only going to look at binary compounds, which means we're going to look at things that only have 2 different elements in them, bi as in 2. But you can have elements and compounds get together and have lots of different elements in one compound. When we name these things, the cation is named first, the anion comes second, and we change the ending of the anion to IDE. So magnesium nitride is the compound that contains magnesium ion and nitrogen ion. If we wanted to write the chemical formula for it, we would use the symbols. The symbol for magnesium is Mg, and the symbol for nitrogen is N. So that tells us magnesium and nitrogen. Now, these little guys, these are called subscripts. They're written below the letters and to the right. So this says 3 magnesiums for every 2 nitrogen ions. And so the subscript shows the ratio of the ions in the crystal. This one would be 3 to 2. This is actually a 1 to 1 ratio. Now, why would we get 1 to 1 ratios sometimes and 3 to 2 ratios other times? Well, it has to do with how many electrons are being transferred and how many charges it takes to get us back to neutral. So let's look at that in a little bit of detail here. So magnesium and fluorine, this one's a little bit tricky because if you look at this, we're going to start with electron dot diagrams. Magnesium, if you look on the periodic tables in group 2, it has 2 valence electrons. Fluorine is in group 7, it has 7 valence electrons. Now, this is why we always draw these with no side gets 2 until every side has 1. We're trying to get to 8, and we draw it like that. We know there's 1 open spot on fluorine. Magnesium has 2 electrons it can give away. So magnesium will transfer an electron to right there. And that leaves me with magnesium with 1 valence electron and a 1 plus, and fluorine with all of its valence electrons now and a 1 minus, which is fine, right? We filled our electrons and this thing is now stable. It has 8 valence electrons, but magnesium still has another electron it has to get rid of. And so what will happen is another fluorine atom will be here and it's willing to accept that other electron. So magnesium gives off its other electron and we get magnesium with a 2 plus charge and 8 valence electrons, or 0 in this case, right? It dropped to that other energy level. And we have another fluorine ion that has a 1 minus charge. So what we ended up with was one magnesium with a 2 plus charge, and we ended up with a fluorine ion with a 1 minus charge, and another fluorine ion with a 1 minus charge. These guys have all 8 of their valence electrons, and magnesium is down to 0. So this is stable, and so if I wanted to show this in one step, I'd say, all right, magnesium has its 2 valence electrons, fluorine has its 7, and fluorine has its 7, and so I can see one transfers here, and one transfers here, and what I'm left with is magnesium 2 plus and 2 fluorine 1 minuses, and these guys would actually stick together in such a way that we would get magnesium fluoride. And magnesium fluoride would be written MgF2 because we have 2 fluorine ions for each magnesium ion. You'll notice in that chemical formula right there, there are no charges written because the compound is neutral. The chemical formula is talking about the compound. The compound has as many pluses as minuses, so it's neutral. We don't put charges in it. We're going to name this. We use the metal first, which is magnesium, or cation, and then our nonmetal, which is fluorine, and we change the ending to IDE. So this is magnesium fluoride. Let's look at another example. Show the transfer of electrons and the name and formula for cesium and sulfur. So cesium is in group 1. It's got 1 valence electron. Sulfur is in group 6. It has 6 valence electrons. We have a metal and a non-metal. And so we can see this cesium will go here. And then we're going to need to fill in this open spot as well. Sulfur has 2 open spots. So another cesium can go ahead and do that. So what we end up with is a cesium 1 plus, and a sulfur 2 minus. We need 2 cesiums in order to do this. So our final formula is CS2S. Cesium sulfide is our chemical formula. Cesium, the name of our compound. CS2S is the chemical formula. Cesium sulfide tells us what we have. The ratio of ions is 2 cesiums for every sulfur because we took 2 electrons and cesium only has 1 to give to get sulfur to its stable electron configuration. A couple more. So let's take a look. Aluminum and oxygen. If we start with aluminum, it's got 3 valence electrons, 1, 2, 3. Oxygen has 6, 1, 2, 3, 4, 5, 6. Okay, this looks like it's going to be tricky, but it really, really isn't. We know aluminum has to give away all 3 of its electrons. And so we're going to end up with an aluminum with a 3 plus charge. And we have oxygen, which has a place to take 1, 2 electrons. So we're going to end up with oxygen with a 2 minus charge. And this will be all 8 valence electrons filled in. Now, if I have a 3 plus and a 2 minus, they have to get neutral. That means I need a ratio that ends up 0. We could do the math, but what works is if you take that charge and cross it, and this charge and cross it, and use those as subscripts. And what that shows us is if we have Al2O3, we have a neutral compound. Now, just to double check, Al2 means 2 aluminum ions. Well, 2 aluminum ions each have a charge of 3 positive, which gets me a total charge of 6 positive. 3 oxygen ions each have a charge of 2 minus, which gets me a total charge of 6 minus. And so 6 plus and 6 minus adds up to 0, and this is the ratio of the neutral compound. So Al2O3 is the chemical formula, and the name is aluminum oxide. Remember, change that ending to IDE. A couple more real quick. Potassium, K, which is going to have 1 electron. Nitrogen, which has 5. And so we can look at this and say, okay, we're going to have potassium with a 1 plus charge. Nitrogen will form the ion with a 3 minus charge. It has 5, it's 3 short of 8, which means our formula is going to be K3N, and our name is potassium nitride.